Hello again, this is Ron Rinkenbach from Introspect Technology, and today I'm going to be demonstrating SV1D production module interoperability with a commercial MIPI D-PHY receiver. And we'll start by looking at the hardware. If you'll take a look on my screen, I have a webcam, and over here is the hardware we're going to be using for this demo. There's two groups of hardware. The group on my left, right here, is the Introspect solution. It's composed of three elements. At the heart of it is the SV1D production test module. Right here, you can see the gray is the heatsink for the SV1D module, and I've got that module installed on the bottom of the PCB because on top of the PCB I have my high-speed connector, which takes these high-speed signals and brings it to a second box, which we call the SV1C MIPI. And the function of this box is to take the high-speed signals and to take some LP signals here, and it's a combiner. So it combines the signals to generate the MIPI signal, which is here on this blue wire. For this particular demo, I'm going to be using one clock lane and two data lanes, so a total of three diff pairs. And I'm going to be feeding those into this little adapter board here, which is basically an SMA to ribbon cable converter. There's no active components on this. It's just a question of routing the signals. And the reason I need to route it onto the ribbon cable is because on the other side we have our commercial device, which we're going to interop with, is basically a single board computer, has the same type of ribbon cable as us, and what we're going to do is we're going to interop with this single board computer. Basically, it's a Freescale processor on it. The single board computer is called the IMX6. It has a bunch of connectors around it, a bunch of different interfaces that are supported. Worth noting is this HDMI interface, which is going to be used to power this monitor right here. And then of special interest is, of course, this a little connector right here, which is the MIPI bus. It's a MIPI D-PHY. And right now it's connected to a commercial MIPI D-PHY camera. And what I'm going to be doing is I'm going to start up the single board computer and get the camera streaming to the processor, and then the processor will output the video stream onto the display. And then once it's doing that, what we'll do is we'll disconnect the camera and connect the Introspect solution and get the Introspect to stream some images onto the display. But before we do that, I just want to take you through our software environment. So I'm showing on my screen right now the software environment, and you could see that it's the same environment that we use for many other applications. For today's demo, we're going to be doing the MIPI D-PHY. So I have a special component here called the MIPI D-PHY generator. I've got that instantiated into my component area, and it has a number of different properties that need to be set to set up the hardware. So you have your data lanes properties. For this demo, I'm only using 2 lanes, but this could go up to 4 lanes. Going to be using a data rate of 800 megabits per second. I have a pattern file here. I'm going to be initially sending the CPS Colorbar pattern. This is the pattern that's specified by the Conformance Test Suite by MIPI Alliance, and so we'll be sending that. I'll get into a little bit more details about the pattern generation later on in the demo, but for now we'll just make sure we specify a file name in there. And then under that, we have a bunch of analog controls to control the hardware. So I have 2 properties here for the HS data. This is the high-speed data signals. Continuing on with the property description. So HS data, we control the common mode voltage and the voltage swings. We also have two controls for the LP. So LP data, the high level and the low level on the voltages, also scalable and controllable. Same thing for the clock. So clock, common mode, voltage swing, LP low, LP high on the clock. And then after that, we have some pre-emphasis or de-emphasis taps for both the data and the clock. And finally, we have some skew parameters, which allows us to control the skew between the clock and data lanes. Okay. So now we're ready to power on the hardware and execute these CPS Colorbar pattern. I'm just going to go ahead and click on the Run button down here. And the first thing that the software does is connects to the hardware, then it compiles the pattern file, and then actually sends all that voltage information and pattern file to the hardware, all that in about 2 seconds. And so at this stage of the game, the hardware, the MIPI SV1D MIPI module is transmitting a valid MIPI images, just that we can't see it because it's not hooked up yet. So what I'm going to do now is I'm going to power on the single board computer, and we're going to start streaming from the MIPI camera. And after we establish the streaming, I'm going to disconnect the camera and plug in the Introspect solution, and we should be able to see some valid images on the screen. So I have this little terminal window which is connected to the single board computer, which will allow us to see and control the single board computer. Let's start by powering it on. And then if we look on the screen, we see a bunch of text going by. That's just the normal boot process. You see the monitor just came alive. Again, the monitor is controlled by the single board computer through the HDMI port. And now I'm just going to log in. And I developed a little batch file which enables the streaming program. There's two video choices. One of them is for the MIPI camera, which is number 2. So I'm just going to go ahead and select the MIPI camera. And as you can see, there is an image on the screen, and it is in fact the camera streaming, because you can see as I move my hand back and forth, it is in fact a live stream. So at this stage, we're ready to disconnect the camera and go ahead and connect the Introspect MIPI bus, and there it is. So this is the CPS Colorbar that we defined in our test procedure right over here. So this is the pattern that we're currently sending. If I want to change that pattern, I've developed some other patterns. If I take a look over here, I have a pattern here called my all white pattern. And so what I'll do is I'll go ahead and specify that one by typing it in here, my all white pattern. And I'm going to go ahead and run that. And as I do, let's keep an eye on the monitor here. We should see the pattern change from the color bar pattern to the all white pattern. So there it goes. So pattern was compiled, and we get to see the new pattern on the screen. So I guess the only thing left to go into the details of is the actual construction of the pattern file itself. So let me bring one of those up. It's quite simple, actually. This is the all white pattern that I just sent. This is the file that I used to create that pattern. This is the whole file. It's a total of about 50 lines. And there's basically 3 sections to this file. The first section is a frame start. The second section is to describe the actual image that we're sending, and then a third section which just does a frame end. These are all MIPI packets The first section and third section are what MIPI short packets, that's what they call them. And then in the middle here, we're transmitting some MIPI long packets. And I could just go into the details a little bit here. The frame start, there's this command called control HSDT SOT. So control is just specifying that this is a control command. And HSDT stands for high-speed data transfer. SOT is start of transmission. And this happens to be a very powerful command. With this one command, when the compiler compiles this pattern, it does a lot of things for this one command. So what it does is it takes it from the LP state and drives it into a HS state, such that the user only has to specify which bytes he wants to transmit in high-speed mode. So the control HSDT SOT command takes the signal from LP11, transitions to LP01 to LP00, does the HS prepare, inserts the HS0, and then inserts the SOT marker. All of this is done with one command by the compiler, and then the user goes ahead and specifies the short or long packet. So in this case, it's a short packet with a data identifier of 0, which just means a frame start, and also computes a ECC, which we insert at the end of the data transfer. So once the frame is started, then we can specify what we want to transmit as an image. So if we take a little look at the middle section here, you can see that I'm looping for 480. That's because I forgot to mention that the actual image size that I'm transmitting is 640 by 480. So I'm going to loop for 480. In other words, I'm going to define 480 lines in here. And so each line is described by a long packet. And in the long packet, the structure is a little bit different than the short packet. In the long packet, you have a header, and then you follow it up with a payload. So in the header, we're going to look at some details here. We have this command called HSTX, that's just to transmit a byte. And the first byte we transmit is 1E, that's the data identifier for the long packet. And 1E happens to be for a YUV 422 8-bit encoding format. The next 2 bytes specify the byte length, the packet or the payload size. In this case, we have a word count of 1280. For this encoding format, there's 2 bytes per pixel. So a word count of 1280 actually corresponds to 640 pixels. So that's where our 640 by 480 comes in. So we're going to repeat the payload 640 times, and then we're going to follow that up with the CRC or the checksum. That describes the long packet, and then we're going to go ahead and loop that 480 times, and then we're going to go ahead and issue our frame end packet, which is the same as the frame start packet, but with a different data identifier, in this case 01, which indicates that it's a frame end. And so this whole structure, this structure is for one image. This whole structure, if we look at the top, gets repeated in something that we call a main loop. And then in this particular application, we're repeating it an infinite amount of times. So this thing is continuously streaming the image, which is good, which is a good way to test a DUT. So basically, what we're showing is very powerful, very high-level commands that allow you to focus in on the details of what information you want to send in the packet, and then save this to a file. In this case, I saved it to a file called myallwhitepattern.csv. CSV is a comma-separated values file, and you can use any text editor to create these type of files. So Once the file is created, we go inside the GUI and we specify the file name, and then we just go ahead and click run. So I'm just going to change the image again, do another little interop test here, and I'm going to put back the CPS Colorbar pattern. I'm going to go ahead and click run, and keeping our eye on the monitor, we could see that we just changed the pattern again. So that pretty much summarizes what I wanted to show you today. Just to go over what we did is we did prove that the SV1D module does interoperate with the third-party hardware. The third-party hardware we use today is the IMX6 Freescale processor, and all this through a MIPI D-PHY bus operating at 800 megabits per second. Thanks for joining me. Hope you enjoyed the demo. If you have any questions or want to get some more information, we invite you to visit our website at www.introspect.ca. And thank you very much for your participation, and hope to talk to you soon.